Our next speaker is going to be Waleed Ammar from AI2. I'd like to request Matt Gardner on the stage to introduce Waleed. Thanks.
Awesome.
So this is Waleed. I first met Waleed when we both started at CMU at the same time. I think we were about the only two PhD students in the program, or grad students with kids, which was exciting, so we became friends. I guess we both ended up after CMU at the Allen Institute for Artificial Intelligence, and I helped convince Waleed to come. And we've had a good time working together there. We recently started, I guess it's been almost a year and a half, we started a podcast together, which I know some of you have heard. Had a lot of fun with Waleed doing that. And for about 2 years, he was leading the research team in the Semantic Scholar team, which is trying to build knowledge bases from the academic literature. And Waleed recently handed that leadership off to Dan Weld, but I think you're still going to be here talking about Semantic Scholar stuff. So, welcome.
Thank you, Matt. So I'm super excited about scientific literature, and I wanted to share with you today why I think this is an important and interesting area to work on, and also try to hopefully convince some of you to join us in this battle. As you probably know, the scientific literature is growing, but it's just it's fascinating to look at the exact numbers. And a couple of years ago in KDD, Yuchua, Dong, and other colleagues at Amherst published this paper at KD, and like you can see on the x-axis, the year papers are published, and on the y-axis, the log of the number of publications, new publications. The amount, in a couple of years, we're probably going to be at 10 million papers, new papers per year, and that's just it's massive, right? And it's hard for us to imagine this because none of us work on all research areas at the same time. So let's look at a smaller number, just focusing on NLP. A couple of weeks ago, the ACL co-chairs published this figure showing the number of submissions to ACL. In 2019, we got about 2,900 submissions. That's 10 times as much submissions as we did 20 years ago, and twice as much, almost twice as much as we did last year. So it's pretty crazy what's happening. And in many ways, this is actually something that we should be happy about, right? These scientific publications are talking about developments that are transforming our lives. And so just to mention a few examples, there's CRISPR, there is Google, there is Mechanical Turk, there are neural networks. Just these are the tip of the iceberg. And also, when you look at the global life expectancy, it's going in the right direction. People are recognizing that research is making their life easier, so we're not just living in a bubble and endorsing our own contribution to the world, right? So we have a lot to be happy and to be proud of, but also we have a lot of papers to read and to review and to build on and to compare to. So it can be overwhelming. And yeah, every time one of the NLP conferences publish the accepted papers every year, I think people stop working, please. We don't have time to read all these papers. So one question I think we need to ask ourselves often is, can we make similar progress in science without actually publishing as many papers? I think the answer is yes. I think it has to do with the incentives that are giving to researchers to do their work. Many of them revolve around number of publications. And we all know this is not the best metric, but we all still use it when we're recruiting, when we're graduating students. And it's really not a computer science question, so I'm not going to talk about this today. Instead, I'm going to talk about a more modest but more actionable question, which is how do we cope with this growth in the literature, and how can AI help? So we asked researchers in different fields how they do this, and we got a few answers. One of them is relying on research aggregators. So For example, Sebastian Reuter has this website, NLP Progress, where he tracks data sets in NLP and the latest results on these tasks. And then, as Matt mentioned, we have been working on this podcast for a while, and we find interesting work. We invite the authors to talk about the work. So you can do this. Some problems, this is that people have biases, and you're adopting the aggregators' biases by just like relying on them. They're also like interested in different things than you might be. Another thing that you could do is follow a bunch of researchers that you trust for some definition of trust. So, for example, in Span Scholar, you can add a few alerts for people that you would like to follow, and every time one of them publishes a paper, you get an email about it. Also, increasingly, Twitter is becoming a place where people advertise their work. So, just like the other day, Manal Farouki was advertising his paper at NACL, at ACL. The problem with this is you're creating an even smaller bubble for yourself by just like looking at researchers you already know and you trust. And this is giving yet another place where people who are well-known, research labs that are already well-known, are getting advantage. Another approach is to just like take it all in, right? Every day, open your email and check all the archive publications. And I know some people who can do this. I tried. It's not for me. But yeah, it's one way people do things. The problem is like this takes a lot of time, discipline, and also it's impractical. It's not just like that you're scanning the titles, but you also need to add them to a reading list, and then you need to actually read the paper at some point. And then there's research, right? When we're working on a problem, we need to do a literature survey, and we still do this. In practice, we do all of them. They're useful, they're complementary, but they're not enough. And then this is where the superhero comes and like saves the day, right? It's not quite like that, but that's what we would like to think. So some examples of places where we found AI to help in this problem: identifying missing citations before you make a submission. So last year, Chandra and other colleagues at AI2, we developed this model for predicting which citations are missing from your paper. Like the innovation here was like finding a way to use the content of the paper, the entire paper, to improve the recommendations. Another place where this AI could help significantly is peer reviewing. We do a lot of peer reviewing, thanks to the 2,000 submissions in ACL, almost 3,000. But yeah, and there is not much data to work with. So last year we published this data set of peer reviews. Some of it came from the Open Review platform. Some of it came from the SoftConf by discussing it with conference chairs. And this year, a bigger data set is being published as an extension of this work. And then there's also like things like archive sanity. I'm sure some of you heard of it. And we're building a recommendation system at Span Scholar, and we'd like, if you'd like to beta test it, you're welcome to do that on this link. Happy to send it to you later if you email me. And then, of course, we can improve search. So a couple of years ago, we worked on a way to encode the knowledge bases, the knowledge graphs of entities to improve the search for scientific documents. But today I'd like to focus more on the knowledge base side of things. So these are some questions or some tasks that we routinely do as researchers, which can benefit from having a structured knowledge base of the literature. So examples of these tasks include finding papers which compare to some method or some other paper, recruiting reviewers for a given area or a paper, finding other papers that use some method for some task, and actually reading the tables and figures in a paper. So I'm going to next talk about literature graph, which is Span Scholar's knowledge base for scientific documents, what it is, how we construct it, and some example application of how we find it to be useful. So we start by creating a node for each paper in the literature, and then we find the authors of those nodes and create nodes for them. We identify the citation links between papers and add them to the graph. Then we would like to actually understand or classify these citations to make sense of, is it extending the work? Is it comparing to a previous model that was reported in the paper? And then we'd like to extract the entities and relationships between them and link them to an existing ontology of scientific concepts. And we would like to extract tables and figures because we realize that a lot of people use figures and tables to just like be a quick summary of a paper. And finally, we would like to add external content that's not listed in the paper, but it's related to the publication. So we link the papers to clinical trial records, to GitHub repositories, and YouTube videos about it, and Twitter conversations. Now, how do we build this literature graph? Actually, the individual sub-problems that I described earlier are pretty easy. Like, they're not necessarily easy, but at least the NLP literature, I've been working on it for a long time. So we know how to solve the problem if we had data. But the culprit is that we don't have enough data, and annotating in this in scientific documents requires someone who actually can understand them, and that researchers typically don't want to spend a lot of time annotating papers. So I'll mention a few places or a few problems where we managed to find solutions for this problem, and I would like to share it with you. One of them is citation intent classification. So here, the problem is, given the context of a citation, we'd like to understand whether it's describing reuse of a method that was published before, or is it just mentioning this paper because it's related and otherwise the paper may be rejected, or you would like to acknowledge the previous work. So here, the biggest data set that was available is about 2,000 instances. Most of them was in the background category, which is not particularly useful. So the idea that we had was to use structural scaffolds. So a scaffold task is a task which you don't really care about, but it's related enough to the task that you actually are working on. So and you also have a way of generating massive amounts of data for it. So in this case, citation worthiness is just like, you look at a sentence and ask yourself, should this sentence be citing something? And you can remove the citation marker and then have a model predict whether there should be a citation or not. The next one is section titles, which we found to be very correlated with certain categories of the citations. So the results show massive improvements in the performance from 54 to 67 when we add these two tasks on top of the previous state of the art. And then another problem where we also didn't have much data is extracting scientific entities. We pulled together all the data sets that were available at the time, and there were not much. So Matt Peters came up with this brilliant idea of using RNN language models to featureize the words and provide a contextualized representation, which turned into Elmo in a subsequent paper, and it's really something that benefited a lot of other research. So another problem where we also needed to find ways to augment our data is extracting figures. There we didn't have any labeled data. Noah Siegel came up with this idea of manipulating LaTeX source code in order to draw a box around each of the figures and tables, and then you can first render the image, render the paper without the modification, and then render it again with the modification, and subtract the two images to get exactly the label data that you want for your problem. And finally, in this problem where we wanted to improve the entity coverage, so a lot of work focused on improving the relation coverage in a knowledge base, but in scientific ontologies, a lot of the time, the rate at which we're defining new terms are faster than the rate at which we're curating this in the knowledge base. So we also want to be able to find these new entities and add them with their definition. So in order to do this, we found that one way to do it is learning from the definitions in the papers for entities we already know about. So we do this by first linking the entities that we know about to a knowledge base, and then find for each sentence where the mention appears, is it similar enough to the definition in the knowledge base? If it is, then we add it to a set of positive examples. If it's not, we add it to a negative example, and then we have annotators re-annotate these examples. We don't just like go and show them all the mentions because it would result in 99% or more of negative examples, which is a waste of everyone's time. So the result of this was a data set of about 750,000 positive instances. Now we have this literature graph. What do we do with it, right? One thing that we did is use the literature graph to enrich the features we have on Semantic Scholar. So now in Semantic Scholar, you can open a paper and find the videos related to it. You find the images. So sometimes even if you don't have access to the paper, you can still see the results and understand something about what the paper is talking about. And then we also list the entities that we extracted from the paper, among other features. But beyond Semantic Scholar, we now enable researchers to compute over the literature. So I'd like to walk you through a quick demo here to show how this works. So here, these are just some examples of queries that you can use. So I'm going to start with this one. Here we're trying to match authors who wrote a paper P, and this paper mentions the entity relation extraction. So let's just like remove any constraint here just to simplify the query as much as possible. And yeah, we're counting the number of publications for that author and listing their first name and last name. So here you get a long list. I think there is. Yeah, so that's why we needed to order. Order. Right, so this is the list of like the people who publish the most on relation extraction since forever. So if we want to only people who have been working on this recently, we can add something like where p.year is greater than 2014, and then you get a much a more manageable number of authors, and some of the names here you would recognize. But also you can extend this and say, I want people who work on relation extraction, but also in the same paper, they mention reinforcement learning. And then, again, you see only the people who publish papers on both of these things. So these are queries that you can automate. You can write a script that queries our knowledge base and gives you answers. And there are other, of course, other queries that you can do. So I'm going to show you another one just to demonstrate the Neo4j platform that we're building on, because I think it's pretty cool. I'm going to take this one. So here, if you put this, it gives you a table, but if you modify the query to just return the paper and E1 and E2, so I should say what the query is trying to do. The paper, it's matching papers which mention a first entity constrained programming and another entity that's natural language processing. So we're finding like cross paper that are in the intersection of these two areas. And if you run this, you get skewed graph, which you can manipulate. Oh. Yeah, so yeah, you can just like look at these two entities, and you can modify the query however you want. I think it's pretty fun, and I've been using it when I need to find reviewers for a paper. It actually works. So. Another thing that I'm super excited about, and to some extent is the biggest reason I wanted to work on Semantic Scholar, is I wanted to analyze the trends that are happening in the literature. So one way to do this is to group all the papers that have some property that you care about, you're trying to study, and pick something that's observable. So in one study, we looked at all the pre-published papers on arXiv and looked at the citation rates they have later and found an association of about 60% more for papers that were pre-published. And of course, like, we can't claim that this is causality, but we try to account for as many factors as we could. Another thing that I've been working on recently is trying to quantify the demographic bias in recruiting participants for clinical trials. So here, the idea is to try to understand, because we know that drugs affect males and females in different ways, also different races, we need to make sure that the set of participants in a clinical trial represents the demographic that we care about. And so focusing on males and females for now, the previous studies only looked at very small numbers of clinical trials because they didn't have a way of automating it. So what we did was extracting the tables where the paper described the participants' demographics and their numbers, and then estimate the number of females among patients. So we do this in coordination with the Institute of Health Evaluation, Health Metrics and Evaluations. And then we compute the bias as a difference between these two estimates and aggregate them across all the studies. So if you do this, we ended up with about 43,000 articles, which is a lot more, like at least one order of magnitude more than the previous biggest study, because they had to do it by hand. And then the bias that we observe, we can plot it over years, and it looks something like this for HIV. So in this graph, the bias, the more positive numbers means that there are more, the males were overrepresented. Sorry, negative numbers mean the males are overrepresented. And the two lines here correspond to different ways of aggregating the clinical trials. One of them is to just assume that all clinical trials have the same weight, regardless of how many participants are there. And so that's the blue one. And the red one looks at, gives as much weight as the number of participants in a trial. One of the observations that we found is the blue ones tend to be more biased. So this suggests that the larger studies tend to be to do a better job balancing and having less bias, which kind of makes sense because if you're going to recruit a large number of participants, you have more of a capacity to do that. Another interesting thing we found was by comparing the numbers that we extract from the papers and the numbers that we can get from the corresponding clinical trial records in clinicaltrials.gov, about 50% had different numbers. And this was fascinating. We actually emailed, we went down to each clinical trial in the 100 that we analyzed, and we had to email the authors to understand what happened. Sometimes it's an error, sometimes you report a number in the paper and then some participants drop out and you update the record online. Sometimes the opposite, you don't update the record online, but you only update the paper. So it's really hard to get good estimates for these things. And we only found this by looking at tracking them down. I'd like to talk a little about some of the resources we're sharing with the community to help in this area. I already talked about some of them, but I'm going to focus on Spacey and Seibert. Spacey is an extension of Spacey, which basically retrains the models for the scientific documents and also adds improved algorithms for tokenization. And Seibert is just like a retraining of the Google BERT models for scientific documents. I think it's just 5% of the articles that we have, and it's already more than the original data that was trained for BERT. And these are just like engineering tasks that people don't give a lot of credit for, but they're super important and useful for improving the results. I'd like to also give a shout out to a few resources that we're going to hear about at AKBC, which we found to be extremely useful. One of them is the MAG, Microsoft Academic Graph. When this was published 2 years ago, it had 170 million papers. It's been very useful, the collaboration with the Microsoft Academic team. Iris is going to talk about this in 2 days. You're welcome to join us in the workshop. And then there is a large number of biomedical ontologies worked on by NIH. And Dina is going to talk about one of them, mesh, again in the workshop. And we just heard about med mentions earlier today. It's been very useful for us. It's being published here, but we've been using it for a while. And it's everything that Sunil was saying is true about it, in case you were wondering. And then I'd like to end with just like a few problems that I feel are worth working on, but there's not really enough people working on this problem. So one of them is trying to bridge the gap between doing NLP at the sentence level and doing it at the document level. So oftentimes we define NLP tasks at the sentence level, even though when it comes to applications, we typically use it in the context of a document. And it's not always easy to transfer between these two things. So for example, in entity extraction, you extract entities from a paper, and then you have a whole bunch, like hundreds of entities, and you don't know exactly what to do with them. How do we rank them to show like the most important ones? So one problem that people have been working on recently is entity salience to find which ones are the most important or salient one in a given document. But I think there's a lot more work to be done there. Another problem is summarizing the published results. And we tried this a couple of years ago. It was extremely hard because there was no data. Recently, the team behind Papers with Code have been annotating and inviting everyone to annotate recent results on tasks. So we actually have some data to work on now, but nobody's working on it. And then we would like to develop better tools for peer reviewing. There's now data to actually do this, and some vacuum. And then we would like to find ways to improve the quality of annotations on specialized domains like scientific documents and legal documents. I think this is, if we find a way to do this, it's gonna be very transformative in a lot of problems. And then finally, we know how to judge papers a few years after they're published, but we would like to be able to judge them sooner, a lot sooner. So if there's some work that we did before in predicting the paper impact, there's a long way to go in trying to do this. To wrap up, you're not alone in struggling to keep up with this literature. An enriched knowledge base can help, has helped the researchers to explore this, the literature more effectively. And we are a small but growing community, so please join us. Thank you.
We have time for a few questions.
Do you have any way of evaluating the novelty of a hypothesis in a paper? So in an experiment, right, there is this underlying hypothesis, and some experiments are much more novel than others. So even if you have, a study that's much larger than others, it's not necessarily worth all that much if it's a relatively non-novel hypothesis. Do you have a way of, obviously it's very difficult because how, if you're just at the level of extracting entities and relations, how do you define novelty? But I'm just wondering whether or not you've considered that problem.
Yeah, we didn't try to address this problem in particular, but we have data now that we can use to evaluate a model that does this. So some of the part of the data that we have in the peer read data set is annotated with every paper. You have the paper, you have the review text, and you have the originality score that was assigned by the reviewers for this paper. So if someone comes up with a model that can do this, we can at least evaluate it.
So at this point, what you have is you have a quantitative number for the novel. You have the number for the novelty based on the reviewers, what the reviewer says, but that's not necessarily sort of the distance between what the theory was before. I realize this is very far out, but it's kind of really interesting also, right? Because that's really what you want to know.
One
of the things you really want to know.
What's like the ground truth is hard to tell, right? But
yes.
I think relying on the peer reviewers whose job was to review this, in volunteer capacity, to review this work, I feel like that's a reasonable.
Oh no, for sure it is. But it's just sort of, it doesn't kind of get at what the novelty is. But yeah,
right.
I'm just just curious as to whether you're moving in that direction. Okay, thanks.
Thank you.
Any other questions? So I have one, I guess. So you worked with, like you guys do papers, but there are many different scientific fields, and a lot of your methods are general, which is great, but have you seen huge differences between, say, CS papers and the more bio side of things that you're doing that sort of makes you informed about how to do?
I mean, it typically depends on the data availability. Oftentimes, the data is more available in one than the other, and we try to bridge this gap, but it's never easy because like the set of annotators who care about this are different, and yeah, we often do have this discrepancy.
But in terms of your methods, are they any different across?
The methods have been typically, when we had the luxury of trying both, or like different fields, we got consistent results for the most part.
All right, let's thank Waleed again.
Thank you.